Hey guys, Mr. Backerberg here. In this video, we're going to look at graphical models. A graphical model is a visual representation of either a numerical or algebraic model that gives us some insight into the relationships between different quantities. In this first example, we're going to look at an experiment that Galileo would have done back in the late 1500s or early 1600s. Galileo spent a lot of time rolling balls down inclined planes, and what he would do is he would measure the distance that they would travel as a function of the time elapsed. And his experiments are pretty easy to reproduce, so you'll see them done a lot in like physics classes. So I've got a table of values there. The first row represents time in seconds, and the second row represents the distance that our ball has traveled. So at a time of 0, it has traveled a distance of 0 because it hasn't gone anywhere yet. After 1 second, it had traveled 0.75 inches. After 2 seconds, 3 inches. 3 seconds, 6.75 inches, and so forth. So what we want to do is we're going to come up with a visual model, a graphical model of this table. And we're going to use our calculator to help us out. So I've got my calculator fired up here. I want to take that data and we're going to enter it in. To do that, we're going to hit our stat button and we're going to edit the lists in our stat options. So I'm going to hit enter. In list 1 is where I'm going to enter in all of my times. So we had 0 up through 8. So we hit 0, then enter, then 1, enter, 2, and I'm going to keep going all the way up to 8. Now I'm going to arrow over to list 2, and here's where we're going to put in our distances that correspond with each time. So at a time of 0, we had a distance of 0, hit enter, and then we had 0.75, enter, and entering in the rest of the values. So I've got my table filled out. Now what we want to do is get a visualization of what this actually looks like. So I'm going to hit my graph button. And right now there's nothing showing up on there. So I'm going to hit second and my y equals. I want to turn on my first stat plot. And it's going to draw data from list 1 and list 2. So if I hit enter and turn that one on, hit enter. And then if I go back to my graph, I can see a few of my data points, but they're not all in there. We need to adjust our window a little bit. So the easy way to do it when you have information, some data entered into your lists, is if you hit zoom and then option number 9, zoom stat, will change your window so that it will show all of your different data points. And what we want to do with this is try to figure out some sort of graphical model that's going to fit our data. As we look at this, we might have a little bit of experience with quadratic equations or quadratic functions. Those equations have graphs that look like parabolas. These data points sort of have a parabolic look to them as we start at the origin and then work our way out. Galileo also had a lot of experience with quadratic equations, so he theorized that this data could be represented by the model d equals k times t squared, where d is our distance and t is our time. Now in order to use this, we're going to need to figure out what our k value is. So we're going to pick one of our data points. So I'm looking here at the 1 and 0.75. I'm going to take that and plug that information in so that we can figure out what our k value is. So my time is 1, so I'm going to plug that in for my t value. And my distance is 0.75. So if we're solving this for k, well 1 squared is 1 and 1 times k is k, we get a k value of 0.75. So we can rewrite our model with that k value plugged in. So d equals 0.75 t squared. And if we wanted to check to see if this actually worked, we could pick another data point and plug it in. So let's say we looked at the 4 and the 12, and we wanted to double check to make sure that this k value seemed appropriate. So we would plug in the 12 for our distance. We've got 0.75 times our time, which is 4 squared. 4 squared is 16, and 16 times 0.75 is 12. So we get 12 equals 12. And we can actually check this with any of our data points, and it'll work out. So this d equals 0.75 t squared is a pretty good model to represent this data that we came up with. In this example, we're looking at life expectancy based on birth years in the United States. So our first row deals with the years after 1950, and the second row deals with the life expectancy. So 0 years after 1950, so in 1950, the life expectancy was 68.2 years. 10 years later, 10 years after 1950, so that would be 1960, the life expectancy was 69.7. And you can see as we go on from there, it looks like that life expectancy is gradually getting larger. We're going to take this data and enter it into our calculator. We've still got our information entered in there from our last example, so I'm going to hit Stat, and I'm going to go into Edit. We need to get rid of this data that's currently in our list. Now we have to be very careful as to how we do this. If I want to get rid of the information in List 2, I'm going to arrow up to the top, and what I'm going to do is hit my Clear button and then Enter. Do not hit the Delete button. You will delete the entire list. If we want to get rid of the data in List 1, we arrow over there and we arrow up to List 1. And again, hit the Clear button, not the Delete button. And then hit Enter. So now we've got some empty lists, and we're going to fill them up with that data that we had. So we're going to take the years after 1950, and that's going to fill in our List 1. So we had 0 up through 60, counting by tens. And then in my List 2, I'm going to type in all of the corresponding life expectancies for our List 1 data values. So I've got all of my data entered in. If I hit the Graph button, our stat plot should already be turned on from before, but there's no data points showing up because we haven't adjusted our window yet. So I'm going to hit my Zoom button and then option number 9, Zoom Stat. There's all of my data points. Now in the first example, our data points had sort of a parabolic look to them, so we ended up coming up with a quadratic model for that. This one, our data points look a little bit more like a straight line, so I think maybe a linear model would be a little more appropriate. So things that are linear look sort of like y equals mx plus b. First thing we want to find is our m value slope. And I'm going to use the starting and ending points of my line. So I'm going to use this set of data. So the 0 and the 68.2 is one ordered pair. And I'm going to use my last piece of data as well, the 60 and the 78.7, as my second point. Remember, our slope formula is y2 minus y1 over x2 minus x1. So if I plug in my information, I've got the 78.7 minus the 68.2 all over 60 minus 0. If we simplify that down, we get about 0.175 as our slope. So we can take that and plug that into our equation. So we get y equals 0.175 x. And as far as our b value, the b value is the place where our line is going to cross through the y-axis. So when our x value is 0, what's the y value there? Well, it's the 68.2. So we're going to put plus 68.2 on the end of that. And now I'm going to go back to my calculator. Now I'm going to hit my y equals button. And what I want to do is type in that equation that we just came up with. So 0.175x plus 68.2, and I'm going to graph that out along with my data points. And my line is really close to most of those data points. There's really only one that's kind of a little distance away, but it's really close to all the other ones. So we could say that this line is a pretty good fit for our data that we're dealing with. Now, a statistician might take a look at this and say that we've got one data point that doesn't really fit our model. So they might try to investigate that a little bit. And that actually ends up being the year like 1970. So they're going to look at some data from 1970 and figure out why there was that dip in our data point. And another thing to consider, our model's not perfect. This line is going to keep extending out forever and ever and ever, but we know that life expectancy can't keep increasing infinitely. There's a limit to how long humans can actually live. So while this works for the data that we're dealing with, we could predict values in the middle, it might not be so good as we keep extending out forever and ever. So if we wanted to look at predicting future data, we might have to come up with another model. But we're not going to worry about that right now. So that's going to be it for this video. Thanks for watching.